As you know, you're here on day 3, Unlocking the Mysteries of the Universe. We've talked about, are there other worlds out there with Lisa Kaltenegger, and we then used our imagination to think about how we have imagined other worlds and how we imagine other worlds. And now we're actually taking imagination and trying to make it a little bit more tangible, but trying to understand how we grasp the sheer vastness of the universe. We'll be doing that in the hands of an amazing astronomer and educator who is sitting with me right now. His name is Phil Sadler. I'll be introducing him, and he'll be kicking things off momentarily. I did want to remind you that we are closed captioning today's event, so you can watch those captions appear on your screen. If for any reason you'd like to turn them off, you can click on the CC button and click on the display option and choose none, and you can toggle those on or off as needed. And don't forget, we do want to hear from you, so submit questions or comments at any point. Phil has a number of questions for you, and we'll be looking to hear your answers as we go along. Also, the recordings of all of our sessions during the Smithsonian Education Online Conference are posted in the program area. All of our Part 1 sessions are there, and today's sessions will join them shortly after we finish today's events. Don't forget, the conference continues tomorrow, and we'll be exploring the theme of biodiversity, and you won't want to miss our discussions, which will take us deep into the rainforest and exploring animals and organisms that most people never see. So do check that out as well. That's tomorrow. Don't forget, our conference is brought to you by Smithsonian Education with support from the Smithsonian's Office of the Chief Information Officer, and I'm with Learning Times, and we're happy to play a role here helping to host and produce the conference. So thank you all for being here. Finally, I would like to thank Microsoft, Partners in Learning, who have helped make this program possible. So with that, please join us as we start to wrap our hands around what it means to think about the sheer size of the universe. And our guide in this endeavor is Phil Sadler, who is actually the head of the Science Education Department at the Harvard-Smithsonian Center for Astrophysics up in Cambridge. He's also a senior lecturer at Harvard in the Department of Astronomy. Phil, thanks so much for being here with us.
Happy to be here.
Let's talk about the problem that we face during this problem-solving session, which is really grasping the vastness of the universe.
Well, I study the human understanding of astronomy, both the difficulties that scientists have in trying to figure out what's happening up there in space, and the similar difficulties that students or learners have in understanding the universe. And today we're going to cut the universe down to size and try to make it fit into our daily experience. So we're going to do this by examining the power of models in advancing our own understanding. So the next slide, there we go. So our minds really have considerable limits, and the size of objects and distances in astronomy are so huge they're really hard to imagine. So we're going to select some specific systems and model them and try to figure out what new we can learn by using a model instead of the actual objects. And one way I like to start is that I like to start off my classes with a quiz. So I have tasks for both students and teachers who are watching, and different tasks for each. So I have a 3-question quiz to sort of start off and try to figure out what it is that you think right now, and maybe some of it will change as a result of the next hour. So if we go to the first quiz question.
Let's bring it up. So, Phil, we're putting this question up on the screen. It's
okay.
a multiple choice question. Let me make it, I'm going to make it a little larger here for everyone
All right.
to see it.
So we're going to start off with a simple model of a basketball as the sun. So we see the sun in the sky. It looks pretty small, and we're going to model it with a basketball. And if we had the sun as a basketball, where would we put the Earth in the same scale model? So
we're all picturing a basketball. We're imagining that's the sun.
Yeah.
And if the Earth were to scale, how far away would it be from that basketball?
That's right.
Okay, so we're getting your votes in. We're hiding the results right now because we want you to think independently. How's that?
Okay. Well, and for the teachers in the group, the question is a little more complicated, which is not what the right answer is, because presumably all of our teachers know the right answer, but what is the most common wrong answer that that people report. So teachers should look at this and figure out what is of the people answering this question, which of the wrong answers is the most popular.
So how about this, Phil? I'm going to go ahead and show people the results. We'll lock them in, and we'll come back later, and you'll tell us how we did.
Okay.
All right, there's the results. Interesting. Okay, should we go to question number 2?
All righty.
Okay. So here's question number 2. You want to explain this one?
Yeah, this is a similar model, but in this case, there are 5 options. The left-hand circle is the Earth, and the circle on the right is the Moon. So we have 5 options of the difference in size of the Earth and the Moon, and the difference in distance. So so the Moon varies. There are 2 different sizes and 3 different distances. So if we shrunk the Earth down to the circle on the left, which would be the appropriate scale for the Earth and the Moon?
Okay, and the results are coming in from...
Oh yeah, I see them. People are voting.
So take just another couple of seconds, look through those choices, and then just click the circle next to A, B, C, D, or E over on the upper left corner of your screen.
And for teachers, it would be good to write down which they think is the most popular wrong answer for students.
Okay, I'm going to lock in the votes in 5 seconds. Here we go. 4, 3, 2, 1. Okay, so we've got the results up. All right, there are the final choices. We'll come back and revisit this question after Phil takes us through some ways of modeling and thinking about the universe. Should we go to question number 3?
And finally, question number 3, which has to do with the solar system.
Okay, there's question number 3.
So here we are on the Earth. There are 3 objects, the Sun, Saturn, and the Moon listed, and the goal here is to go from the closest one to the farthest away.
Okay, closest object to the Earth to farthest from the Earth.
Right.
Okay, so work through those 5 choices, pick the one you think is correct. And I suppose teachers should also think about what they think people might get incorrect on this.
Yeah, which is the most popular wrong answer, which we find to be very useful for teachers.
Okay, great. We're going to go ahead and close this poll down. 5 seconds. And we've got the results on this one too. So there you go. Okay, interesting.
Okay, so now people have voted, and by the end of the session, we'll revisit these questions and see if there's been any changes in people's understanding or people's answers. So we're going to start off with the 2 difficulties that are particular to astronomy. First of all, in astronomy, the objects are enormous. So the things we're used to in our daily lives are like other people or things we eat like oranges, cars, tiny things that we may hold in our hands. But in astronomy, everything is much too big to actually imagine. We can talk about them only because they're so far away from us that we can point to them in the sky. So the objects are huge, and to give you an example, we're going to use an orange, a 3-inch orange as our standard. And if we wanted to model the Earth as an orange in our hands, we can look at the next slide. The Earth is we'd have to shrink it down by 169 million times to be the size of an orange, and that's an enormous amount. But if we that's one of the smaller objects in astronomy. An even larger object is the sun, which is the next slide. And the sun would, to shrink down, it looks like an orange. To shrink it down to the size of an orange, we'd have to shrink it by 20 billion times. So that's an even more enormous shrinkage. And finally, if we went to something like our galaxy, the Milky Way, which is roughly looks like a circular object, we'd have to shrink it down. I'm counting the zeros here now. We'd have to shrink it down by, let's see, what is it here? Millions, billions, trillions, by 600 quadrillion times. So for astronomers working on these kinds of things, the number of zeros that they have to carry is enormous. They have some ways to deal with the math with all of these large numbers, but we're going to deal with them by using scale models. And so this is the first problem. It's hard to imagine things that are shrunk down to that level. The second problem is that the distances involved are huge in astronomy. So the kinds of distances we're familiar with might be, driving to the store or even getting in a plane and going somewhere. But on a daily basis, the distances that we deal with are like the distances from your head to your hand, like this cook holding an orange. And that distance is about a yard or a meter that goes from your hand, your outstretched hand, to your eye. And then we can compare these various distances in that way. So if we go to the first example, the distance from the Earth to the Sun would have to be shrunk down 150 billion times in order to reach the distance from your eye to your hand. And the second example is from the closest other star in our galaxy to the Sun. This is our closest neighbor, is about 40 quadrillion times larger than the distance from your eye to your hand. And finally, the distance between two galaxies, our galaxy and the next galaxy, the Andromeda galaxy, is, I don't even know how to say this number. It's just got so many zeros. But again, the sizes are so enormous that it's hard to think about. So we have a couple of ways to deal with these enormous sizes. So now I want to ask some of our listeners a few questions about what their own experiences are in scale models, because we're going to build some scale models here. I'd like to know what kinds of scale models you're familiar with, whether you've built any or use any, and maybe people can message those things in and we'll talk about them.
Absolutely. So go ahead and share with us what kinds of scale models are you experienced using. And you may actually not have thought of them as such. We have a few people saying that they hadn't actually done it, but I have a feeling that everyone has used a scale model at one point or another. We have people who use model trains, model cars, toy cars. We have people talking about doll houses. Somebody whose husband here actually uses war game miniatures and action figures. People who are using dioramas and solar system mobiles. Also looking at cell models in biology, which actually take scale that is smaller and make it larger, versus perhaps what we were just doing, which was making something large smaller. But all of these are scale models, right, Phil?
They are scale models, or they're models, and to be a scale model, the sizes of things should be reasonable when compared to each other, and the distances between them should be reasonable. So, for instance, a diorama of a battle scene, you have little soldiers, and they should be the correct distance from each other as well. Same thing with a dollhouse. You want a dollhouse where whatever dolls you have actually fit into the house and are to scale with the house. So you wouldn't want a doll that's much too big for the distance between the floors in a house, for instance. So same thing with cars and trains. Some model trains are to scale, and some are not to scale. And you can see the not to scale ones look a little foreshortened. They don't look like real train cars. So what we're talking about here are actual scale models where everything is to scale.
And by the way, we're curious, as you think about the scale models that you are familiar with, that you've experienced, we're curious to know what you've learned from using them. What kind of appreciations have you developed? So go ahead and let us know a little bit about that. We have a comment that relational distance is so important.
Mm-hmm.
People who are better understanding the relationship between places by using maps, which is another scale model. Good. So feel free to keep those coming. This is great. Thanks for sharing with us. Okay.
Okay, so I want to talk about the first scale model we're going to use has to do with something that most people know a lot about, which is the Earth as a sphere or as a ball. It wasn't always known that the Earth was a sphere, although some people thought the Earth was flat, and some people thought it was curved, and some people thought it was round. But pretty much all adults now know that the Earth is a ball, and we live on the outside of this ball. We surveyed a group of teachers to find out whether whether their students thought of the Earth like a ball and that they lived on the outside. So that's the next. We're skipping to the next graph. This is the result of, one more slide. This is the result of our survey of teachers about their own students in their classrooms. So we asked the teachers, what percentage of the kids in your classroom think that the Earth is shaped like a ball and we live on the outside? Essentially that ball being a scale model of the Earth. And what you can see from this graph is that by second grade teachers thought that just about all of their students knew that the Earth was shaped like a ball and we lived on the outside. And in kindergarten, maybe about half of the kids knew it, and by first grade, maybe 3/4 of them knew it. So this has to do with whether teachers can predict what students are thinking in their classrooms. Now, after we asked teachers to predict what their students thought, we actually interviewed several students in each of these classrooms to find out what they actually thought, where we let them explain things. We had various props where they could use objects. And what we found was quite astounding, which was that kids actually thought something quite different than their teachers. And that's the next image, which is that in the third grade, only about 20% of the kids thought that we lived on the outside of a ball. And fourth grade, it went up to about 50%, and then it sort of leveled off at fifth grade and beyond. Maybe even went down a little bit in eighth grade, I'm not sure. But the important thing here is the difference between this graph, which we got by interviewing students, and what their teachers thought their students were thinking. And when we asked for deeper explanations about the shape of the Earth and where we live in relation to it, lots of kids in third and fourth grade thought that the Earth was either flat and we lived on a flat Earth, or that the Earth was a ball and we lived inside that ball, in this flat area inside the ball, and the top of the ball was the sky and the bottom of the ball was the Earth. or they had some other view which was not the accepted scientific view of the shape of the Earth and where we live on it. Indeed, into 4th and 5th and 6th grades, even if kids thought that the Earth was a ball, many of them thought that we lived on the very top of the ball, even though there's nobody who lives on the very top of the ball with the North Pole at the top. So there is a big difference between the model that kids have as they're learning about the world and often what their teachers think about the model that kids have about the world. So, and this seems to be a critical issue for learning astronomy, that for teachers, it's very useful for them to know what the ideas are of their students. What we found in our research is that people do understand what a scale model is, but they don't necessarily have the correct scale models for astronomical systems, and they benefit from making these scale models themselves, from constructing them by themselves or in the classroom, and that making these models often changes their ideas. So, as an example of a kind of interview that we did, we asked a 3rd grader to tell us about how she thought of the Earth and the Sun, and to build a scale model for us in real time that showed us accurately the relationship between the Earth and the Sun. And I'd like to introduce you to Lydia, who is going to describe the way she thinks about the Earth and the Sun.
Most of the students we interviewed were familiar with the idea of scale models and knew the order of the planets from the Sun.
All right, here, and you can make an Earth.
10-year-old Lydia is building her own model of the solar system. How accurate is her model?
Okay, so now you said that's
Earth, the Sun.
And do you think it's like the right size for the Earth, or do you think it's
I think
close?
so. It's close enough, because for the Sun, that would be the exact size. If this should be done perfectly to scale, then I would have needed a bunch more Play-Doh for the Sun.
Okay, but and what do you mean by perfectly to scale?
Perfectly to scale means that if everything was really, if Earth was really this small, then the Sun would probably have to be like this big, at least. Mm-hmm. And I would have to move the Earth back at least that far.
Okay. Well, let's try to make it really to scale. But let's leave the Sun this size. So let's leave the Sun this size, and let's try to make it really to scale.
Let's try to make it as close to scale as possible.
Okay.
That means make Earth smaller.
Mm-hmm.
It's like tearing hunks out of continents.
Mm-hmm. Okay. And how about the distance? Is the distance still good?
I think so, because Mercury would be about here and Venus about here.
Okay.
And then Mars would be next, and then Jupiter, and then Saturn.
Lydia has a good understanding of what a scale model is. She knows that it's about shrinking everything down while keeping the relative sizes and distances intact.
Okay, well, that's Lydia describing her scale model. I guess there are two things to learn from that particular video clip. One was that she has this idea in her mind, as did most of the kids we talked to, all the way from kindergarten to college level. They all have an idea about what the relative sizes of astronomical objects are and the distances between them. However, the models that they have do not necessarily agree with the models that scientists have, and that has serious implications. For instance, in Lydia's model, using the model that she has, she could not possibly understand why the sun has, why we have seasons here on the Earth, or why the moon has phases. The model is just too inaccurate to help explain those phenomena. So we're going to build some correct models now.
Phil, can I pause
Yep.
for 1 second? We have an interesting question from Tricia, or someone in her high school class. How can we conceptualize size and distance outside of our solar system? After looking at some of the images that Hubble has returned to us, how can we possibly relate to their location to us?
Well, the location is fairly easy because the location is just some direction in the universe out away from us. It's the relative size and distance of these objects. And the easiest way that scientists do this is they make mathematical models or they make physical models of these systems so that they can understand them. There are physical models of our solar system, of the Earth-Moon system, of our local group of stars, of our galaxy, our local group of galaxy, and of a large portion of the universe. And these are models that people use to conceptualize these systems.
Okay.
It's interesting. I see another comment about going back to the issue about the shape of the Earth and what the shape of the Earth is and whether we live on the outside or the inside. Although many kids have learned this by rote, people have very little evidence that the Earth is actually round. I mean, there are pictures from space, but what did people do 100 years ago when there weren't pictures from space? How did they know the Earth was around? How did they know the Earth was round even 2,000 years ago, well before Columbus? People knew the Earth was round, and they had never traveled around the Earth. And astronomers had proven that the Earth was round and the sizes of these systems from observing, from doing experiments and making observations, some of which I'll show you in this session. So, again, the scale models are very special. They're working models, and probably the most interesting thing about scale models is that the math inside a scale model is the same as the math in the real world. So all the angles in the scale model are the same in the model as they are in the real world. And you can measure distances and relative distances in models and come up with accurate predictions. When I build scale models, they're usually in things like paces and fingers and bricks. Occasionally I'll measure them out in feet and inches and things like that. But I like to use natural scales and natural objects like oranges and other things. So we're going to start off with an orange to represent our Earth. An orange is a really good model of the Earth because if you hold an orange in your hand and you feel the texture of the orange, the lumps and bumps on the surface of the orange are about the same as the deepest valleys and the highest mountains on the Earth. So that the Earth is pretty smooth with some local lumps and bumps. And that's what the Earth feels like. If we look at a picture of the Earth, this looks a little squashed. It's not really, it's a little elliptical on my screen, but we can see that it looks round from space. If we go to a close-up, really close to the edge, we can actually see our atmosphere. So if we look, let's see, do I have a pointer right there? Okay. So if we look at that very edge, that little thin stripe is the atmosphere of the Earth. That's all we have. That's like all the oxygen and nitrogen and ozone and all those things are in that tiny little layer around the Earth. So going back to the orange again, that's the Earth. Let's see, do we have the orange? Going back to the, whoops, let's go back to the orange. Let's see. There we go. Going back to the orange again, that means the atmosphere of the Earth is about the thickness of a piece of paper. And that's all we have at this scale. So now if we leave the Earth and go to space, we've launched many different things into space, like the space shuttle. And the space shuttle orbits the Earth not at a great distance, but very close to the Earth. The space shuttle, on the scale of an orange, orbits the Earth about 1 millimeter away, or about 1/25th of an inch away. It's not like it's some rocket ship that goes out into the stars. It's very, very close to the Earth. It's above the atmosphere, so it doesn't slow down, but it circles the Earth in about 90 minutes, only a tiny distance, about 300, between 150 and 300 miles from the surface of the Earth. Now we send up other things into space. All of you have probably seen GPS receivers. You either have them in the car or you've walked around with them in your hand. And the GPS satellites have been launched and circle the Earth. They circle the Earth about 1 diameter away. So about 3 inches away from the Earth is this so-called constellation of GPS satellites, and they move around a lot. They're all in orbit. They move through the sky, and your GPS receiver has to keep track of which ones are which and pick up new ones when certain ones disappear below the horizon. The communication satellites everyone is familiar with. Anytime you see a dish antenna outside, whether it's a TV dish on your house or a bigger unit on an office or a factory, any satellite dish, any dish-shaped antenna pointed at the sky is pointed at a communication satellite. And these communication satellites are at a special distance from the Earth. They're at a distance of about 4 Earth diameters away. And at that distance, they travel around the Earth. They orbit the Earth in 1 day. Now, the satellites are traveling around in 1 day, and the Earth is spinning in 1 day. So all of those communication satellites are stationary in our sky. Those big satellite dishes or small satellite dishes on your house just have to point to one spot in the sky. That satellite is moving around the Earth, but since the Earth is moving at the same speed, they don't move. So this is quite a distance away from the Earth. It takes a lot of money to put a satellite out at 4 Earth diameters away, and it's a huge investment by the communication industry. And so those are the close things to the Earth. If we want to get a little bit farther away, the next natural object that we have anything to do with is the Moon. And now, at this scale, so there was our Earth, there was the atmosphere, there's the Earth again, and there's the Moon. Now, I like to model the Moon with a grape. So at the scale of the Earth is an orange, a grape is a lot like the Moon at about 4. It's about 4 times smaller than the Earth, about 2,000 miles across.
A quick question from Lisa. So she asks, is the shape of the orbit of a communication satellite the same as the Earth's?
Yeah, the shape the shape of the orbit is in a circular orbit around our equator. All of the communication satellites that use stationary antennas are floating around up there over the equator. So all of those antennas are pointed at the same satellites, and that's very expensive real estate because you can only have a couple hundred of them up there, and you can't have any more. They interfere with each other. So they're all parceled out for different satellites. So anyway, the moon we know is about 2,000 miles across. But we've known the size of the moon for about 2,000 years. So how in the world did scientists figure out how big the moon was?
Let's actually ask people that, and I saw some people with some suggestions for the answer earlier, so we encourage you to jump back in. How did scientists figure out the size of the moon? Let's find out. Go ahead and use the chat box on the left. And I see some thinking going on. Okay, here we go. We've got some answers here. I'm going to hold them back so we can see a few before, so let you think a little bit harder before I start to show you some of the answers your colleagues are sharing. Okay, here we go, Phil.
Yep. Which ones do we have?
Someone has no idea. Maybe witchcraft was involved.
No, I don't think so.
Okay. What about use of a telescope?
Okay. Well, they knew the size of the moon and the distance to the moon before the invention of the telescope. Okay. The telescope was no help.
Now here you go. You've got some people suggesting that perhaps they use. Thank you, Dr. Alegria. They use the other 90% of the brain that we usually don't use.
I see. Well, that could be.
And maybe in doing so, Lisa says maybe they use the shadow of the moon.
Well, the shadow was involved, but it wasn't the shadow of the moon. So that's a really good suggestion. And I'm going to show you how they figured this out, how they figured out the size of the moon 2,000 years ago. And what they did was they waited for an eclipse of the moon. The Earth, like every other object, can have shadows, and there's a shadow produced by the sun, and normally we don't see it in the sky until something happens to move through it. So this is an image. This is a multiple exposure image of the shadow of the Earth as the moon moves through it at night. This happens about once a year, and you can see that there is indeed a shadow of the Earth. It looks like that it's got some curvature. That shadow looks bigger than the moon. Many times bigger than the moon. And I actually have a video here of a lunar eclipse actually taking place. So maybe we can play this video and see what it actually looks like. I wonder if anyone here has ever seen an eclipse of the moon. It takes several hours. And slowly the moon looks like it's being eaten up and disappearing.
By the way, while we watch, Debbie wants to know, when is the next lunar eclipse that she can...
Oh, that's a good question. I should have brought that information. It's usually once a year, and it's visible from all over the Earth. It's not like a solar eclipse when the moon blocks out the sun. This is when the moon moves into the Earth's shadow. You can see the moon looks like it's starting to disappear. We're not going to watch the whole thing. This is usually several hours long, of course, but we can see now it's about halfway in. But I want you to notice what that curvature is, because that's the actual shadow of the Earth that you're seeing. Okay, so this was 2,000 years ago. People noticed this curvature. They didn't have telescopes to look at the surface of the moon, but they could see this curve. Okay, and if we go to the next image, let's see here. They figured that curvature was about the size of the Earth, and it would take 4 moons to fill that curvature of the shadow. And from that, they had measured the size of the Earth. they knew the Earth was about 8,000 miles across, and so the Moon had to be 2,000 miles across. So this was the start of an accurate scale model of the first accurate scale model of the Earth-Moon system. And this was done by a Greek astronomer. But he had another problem, which was we knew that the relative sizes, but how far away was the Moon from the Earth? And that took a whole different type of reasoning to figure out how far away it should be. And this is reasoning that was known. It was basic geometric reasoning, which is you can see a picture of a hand there with a finger outstretched, and I'd like everybody to take their index finger and stretch it out and try to find something in the room that is about half the width of their index finger. So I'm looking around my room here. Well, let's see, nobody's head. Let's see.
I found the number on a clock.
Yeah, and I've got the doorknob from where I am is about half that size. So that something about half the width of your finger is about half a degree across. It also has this very interesting property in that whatever is half as wide as your finger, it would take 120 of those things stretched end to end to reach your eye. So I'm looking at the doorknob, and so I would have to take 120 doorknobs to reach my eye from the place where the doorknob is. Now, this is very useful in astronomy because this is the way they figured out how far the Moon was away from us. Because once they knew it was 2,000 miles across, and they measured it, and it was half a degree across, they knew it was 120 times 2,000, or 240,000 miles away. This was the start of accurate astronomy. This relationship of angular size to the size, angular size of an object to distance. So this is when geometry started to get really important in astronomy. So with that information, we can start to build an accurate scale model. So here we have, for instance, how far the Moon is 120 moon diameters or 30 Earth diameters. So now this is an accurate scale model of the Earth-Moon system. There we go. So if the Earth was an orange, the Moon would be a grape, and it would be way out here. So this is a lot bigger than most people think, and you can see that, you know, if you imagine the sun, if you imagine the sun off to the left of the screen shining on the Earth, then the shadow of the Earth would be way, way out here, and the Moon could pass through the shadow, producing an eclipse. So this is the first scale model of a system that we're looking at, and you could build this scale model accurately in the classroom or in your bedroom, and this would be useful for predicting all kinds of things. Then you can extend this idea to other powerful models like the solar system. For instance, this particular slide shows the sun up here about an inch or two across on my screen, and then these very faint little dots here. I mean, I can see a faint one here and a faint, whoops, let me get my pointer again. There we go. I can see a faint one, there we go, a faint one there, and a faint one there, whoops, there, and the faint one there, that's our Earth, and the faint one there, that's Mars. And these are to scale in sizes to our Sun. This would be Jupiter down here and Saturn here. And this scale model tells you how far away you would have to get to build an accurate model. So if you're going to put that little dot of Mercury that would be about 3 feet from the sun, with the sun being this size. If you went another 3 feet, that would be Venus. If you went another 3 feet, that would be Earth. So Earth, that little dot of Earth would be about 9 feet away from the sun. And to get to Pluto, you'd have to go out to about 300 feet away to get to Pluto. So, and even though we know the sun is big and Jupiter is huge and Saturn is huge, on the scale, on the scale model scale, Jupiter is a lot smaller than the sun. Saturn is a lot smaller than the sun. Now, one of the interesting things I can show here, this, if I go back here, this is a picture of us on Earth looking at the sun with Venus going in front of the sun. Now, Venus doesn't often go in front of the sun, but sometimes it does. And you can see that little spot in the lower right-hand side is whoops, where's my pointer? There we go. Is Venus. And I'd like you to imagine if you were trying to measure the brightness of the sun, how much would the brightness be dimmed by Venus moving in front of it? Well, Venus would start off out here somewhere, and when it moved in front of the sun, it would block out a tiny portion of the sun. If Jupiter moved in front of the sun, it would be, if we could see that, it would be much bigger and block out much more. So let me move on here. And this is a graph of a planet moving in front of the sun, and you can see that there's a little dip in the brightness of the sun, and it comes back up again. And the dip is very, very small. Now, that happens in our solar system. I'd like to now move to our next closest neighbor, our next closest star. So at the scale of the sun being about this size, which is a couple inches on my screen, it's bigger. I mean, if you think of the sun as an orange again, how far away would you have to put the next orange to be the next closest star? So a lot of stars in the sky. Let's pick the closest star to us, and where would the next closest star be on this scale of the Earth being an orange? I mean, the sun being an orange.
And Adam has put this poll up for us, Phil, and there are your choices. So how far away at this scale would the next orange, or our next closest star be? And you can see the results coming in. How are we doing on our responses here?
They look pretty good. They look pretty good. Now, can they see this?
Yes.
Oh, they can see this. So at this scale, at the sun as an orange, the next closest star to us is about 500 miles away. So I flew down from Boston to Washington this morning. So if I left my orange in Boston, I took another orange with me on the plane. And now I have a perfect scale model of the sun and the next closest star. So very far away from each other. So, okay. Now this is an interesting issue. This is about 500 miles. On the scale of our galaxy, it's a tiny. If we are somewhere in on the outside of our galaxy, the next closest star is such a tiny bit away from us. Since there are about 100 billion stars in our galaxy, it's just a very short distance for us, and to go across the whole galaxy would be an enormous distance. So that scale of 500 miles is the equivalent of the two closest stars here in the galaxy. Now, I have a colleague up at the observatory, the Smithsonian Astrophysical Observatory, named David Charbonneau, and every night he has a dozen telescopes that look at stars to see if they're dimming at all. And he's looking for dimming that would tell him that there was a planet going around another star. And his theory is that as a planet went around another star, it would block out some of the light and there would be a dip, just like there was for Venus in our solar system. And the way he does this is he takes pictures of the sky. He has a particular star that he's concentrating on, and all the rest of the stars that are marked here are comparison stars. And he measures very carefully the difference in brightness between this star and every other star in the field. And with those measurements, he can detect planets going around other stars. Now, what he's looking for is something really small. He would like to find a planet the size of the Earth going around other stars. And he hasn't gotten there yet. He's found planets the size of Jupiter and Saturn, and of Uranus and Pluto, Uranus and Neptune, and he's found one planet that's about twice as big as the Earth. But his goal is to find a planet going around another star other than the Sun that's the size of the Earth. So now, how much would, if we go back, how much would that dimming be? Since the Earth is about 100th the diameter of the Sun, its area is about 100th times 100th, or about 100th of a percent. So he has to be able to detect differences in a star's brightness of 1/100th of 1%.
Which means you need to be using equipment where the margin of error is not so small.
He has to use very accurate equipment, and the best place to do this, of course, is not on the Earth, it's in space. And we just launched a big satellite called Kepler that is measuring the brightnesses of stars, of thousands of stars in the sky, to try to detect an Earth-like planet going around a Sun-like star. But we won't know any results for a few years, because just as the Earth takes a year to go around the Sun, these other Earth-like planets will probably take a year to go around their suns. So it has to go around a few times before we're sure it's an Earth-like planet. So anyway, we've looked at a few scale models now: the Earth and the Moon, the Earth and the Sun, two stars, and we've used it to adjust our thinking about astronomical systems. And with this, in your classroom, you can explore phases or seasons or the magnitude of stars or whether space travel is possible using scale models. So I want to return to the questions that we asked early on, and I want to show you some results from a national survey that we did with students in grades 8 through 12. And so this is the Earth-Sun model. The correct, if a basketball was used to represent the Sun, the Earth would be about 100 feet away. And you can see for many students, or this group did a lot better, but you can see that the most popular wrong answer was 25 feet. It was close, but not exactly. People tend to underestimate the distance from the Earth to the Sun, and it's probably from pictures they've seen on television or in books, which are inaccurate. The second question we used was the Earth-Moon model, and this was very interesting because in our the correct answer here is the last image. The moon's about a quarter the size of the Earth, and it's about 30 Earth diameters away. And you can see in the larger group and in our sample of students, that was a very unpopular answer. The most popular answer in our group was D, with about half of the students thinking that the Earth and the Moon are pretty close to each other, but they're actually very far away from each other. And then the last image, the last question, had to do with the solar system model, and here our group did pretty well, although just like in our national sample, many students think that Saturn is closer to us than the Sun. So it's important to get all of these distances and scales correct before we're trying to understand something new about astronomy. But it's possible to build models of all kinds of astronomical systems if you have a good imagination and you have a big enough place to put them.
Phil, thank you for allowing us to realize that our imagination can start as nearby as the closest orange or doorknob or grape, and for helping us begin to appreciate the scale of the world at large in which we find ourselves a very small part. Thank you, everyone who's been sharing questions and comments. We do have time to sneak in one or two questions. I know some of our classrooms joining us may need to move on to other parts of their school day, but we'll stay on for a couple more questions. Let me see what we have here. I did have a few that we wanted to share with you. One question came from Debbie, her class. There's about 20 students watching in Bellbrook. How far can our current telescopes and satellites view in terms of how deep into space?
They can view to the almost to the edge of what we know as the universe. The limit on satellites is on telescopes is really how big is the telescope and how faint a thing can they see. So they don't really bring things closer, they just collect a lot of light. And so we can see objects that are very, very far away, that are very dim if we use very large telescopes.
Thanks, Phil. Here's an interesting question. You were really helping us think about scale models in our own lives earlier. How do mental models that are related to scale help us do other things in life? Are there other examples where you can think about this helping us make some sense of our worlds?
Well, I think they can help with planning. Things like maps are a kind of scale model. So if you're taking a journey, I see my picture up there. I'm a navigator, and so that's a picture of me with a sextant finding my position at sea. A map is a kind of scale model that we use, and people actually make maps. I've made a lot of maps in the past from scratch, which is making a scale model of the world on a flat piece of paper. So that's helpful as well.
Phil, thank you so much for being our guide. I'm sure a lot of people would like to continue to explore some of the resources you've put up here. We also have included a great array of follow-up resources in the exhibit hall. That's part of the SAO area that Phil has provided, so you can see some of the resources that he thinks you would enjoy if you enjoyed today's session. I've also put up a link on the top left of the screen to an evaluation. We'd love your feedback about the session and what you appreciated most about it. So give us some feedback in there, and we do take that into account. Remember, we have the exhibit hall. We also have the discussion area of the site, and you can continue to post your questions and comments in that discussion area. There is an area right below Phil's session on the program page that you used to enter today's session, so do stop by there. Also check out the link, a few links up in the chat area from Michelle Smith here at the Smithsonian Center for Education and Museum Studies. There is a wonderful lesson activity that goes into more detail on the kind of modeling that Phil did with us, and it also features the work of Lisa Kaltenegger, who many of you met when we did our first session today, so I hope you'll check that out. For those of you sticking around for a few more minutes, we'll go ahead and post the drawing that Dan Porter in Kent, England, has been drawing for us during the course of the session. And if you need to miss that, we'll post that to the program page as well. A great illustrative rendition of Phil's session today. Finally, let me thank our sponsors at Microsoft Partners in Learning and here at the Chief Information Officers, the Office of the Chief Information Officer here at the Smithsonian, as well as Smithsonian Education. This is Jonathan at Learning Times. We'll see you all tomorrow. I'm putting up the Day 4 agenda, so we hope you'll join us for more problem solving. We're going to talk about modern animal bones and what we can learn about biodiversity. We'll be also finding out how you can learn about nature's most elusive animals. Not only will you find out how you can learn about them, but you'll see some elusive animals caught well, you'll see them online. The animals weren't caught, but you will see some images of some amazing animals tomorrow from the rainforest with our guide, Joe Kalowski. And finally, how and why do we count living things? Another session into a different rainforest looking at very different types of animals. Check it out. We'll see you then, and thanks for joining us.